All right, let's talk about the modified Atwood machine, but this time we're going to look at it in a couple of different ways. Before we looked at acceleration and forces, now we're going to look at work and energy. And so what we're going to do is we're going to release the cart. Once I pull these weights away, we'll release the cart, and it's going to move by virtue of this mass hanging over the end. And that mass is going to be moving with the cart. Since they're connected by a single string, the velocities will be exactly the same. Their changes in position will be exactly the same. And what we're going to look at is we're going to look at the tension in the string, and we're going to measure that using this force sensor. And that tension is going to do work on the cart, and it's also going to do work on the hanging mass. And we're going to examine both of those aspects of that. In addition, gravity is doing work on the hanging mass. Now, gravity does no work on the cart because the motion of the cart is in the horizontal direction. Gravity and the normal force due to the track are acting in the vertical direction. And so those two forces don't do any work. But the tension is acting in the same direction as the motion of the cart, so it is going to do work. Over on the hanging mass, gravity is going to do work because that force is in the direction of motion. And tension is also going to do work. Now, because the tension is up and the motion is down, the work done by the tension on the hanging mass will be negative. The work done by tension on the cart will be positive, and we'll examine that as well. So I'm going to run this experiment, and we're going to collect some data. We're going to look at position. The motion sensor will find position, but it will also calculate velocity, and from that we'll be able to calculate out kinetic energy. And then the force sensor will tell us what the tension is as the cart moves along the track. So let's go ahead and run the experiment, and we'll see what happens. All right, so our data is collected, and we'll examine that data at this point. What we are working with here is a block and tackle system, and the way this is set up is I have a mass here, and this happens to be 100 grams. And that mass has a string attached to it, and it goes around this pulley, and that string comes around here and goes around another pulley down here. There's 500 grams attached to this pulley at the bottom. Then the string comes back up, wraps around the pulley again, comes back down, wraps around this pulley a second time, comes back up, wraps around that pulley, and then eventually ends up stationary on this set of pulleys down here. And so what you end up seeing here, if I look at this 500 gram mass, there are 1, 2, 3, 4, 5 strings pulling up on this bottom pulley. So 500 grams down here is being balanced by 100 grams up on top. Now there is some friction involved, and we'll talk about that more in just a little bit. What I'm interested in knowing is two things. First off, how much mass do I have to put here at the top in order to begin to lift this 500 grams off of the table? So I have 100 grams currently, and you'll see there's no motion. So I'm going to go ahead and add 50 grams. And if I do that, it definitely moves, and it looks like it's accelerating. So I'm going to bring that down a little bit. So let's try 120 grams. Still not moving. Add a 10 gram mass to that. So here's 130 grams. Still no motion. Finally, we'll put on 40 grams. There's 140, and you can see it falling, and it's got not really a constant velocity, but pretty close. So it took 140 grams to balance 500 grams. All right, now, ideally, because there's 5 strings attached to this bottom pulley, the ratio of forces, or in this case masses, because gravity is multiplied the same on both of them, the ratio of masses should be 5 to 1. 5 pieces of string here, 1 piece of string attached to here. So 100 grams should have balanced this 500 grams here, but it didn't. And part of the reason for that has to do with friction in this pulley setup. And so it took 140 grams to balance 500 grams. Now this has to do with efficiency, and we'll look more at that in just a little bit. The other thing we want to take a look at is distance traveled, because this really goes into work. So I'm going to take a look at, so I've taken off the 40 grams, and I'm going to measure the height from the bottom of this to the table. And as I measure that height, I get a value of 62.5 centimeters. All right, so I want to remember that, 62.5 centimeters. So 0.625 meters. Then when this is all the way to the table, how far is this one off the ground? The value I get here is about 13 centimeters. So 0.130 meters. And one of the things you'll notice here is this ratio, 0.625 to 0.13, is pretty close to 5 to 1. It isn't exact, because my measurements aren't really exact, but it's pretty close. And that really does match up nicely with the 5 strings attached to this bottom pulley and the 1 string attached to the 100-gram mass. The other thing we did not account for is the mass of this pulley. We really should take that into account as well. So I'll see if I can get that piece of information for when I do this on the whiteboard. One of the first things we learn about in physics is a body at rest will remain at rest unless it's acted on by an outside force. Now, these carts have very low resistance by friction, and so there's really very few forces acting in the horizontal direction. And one way I can show that is by actually moving the track underneath the cart. And if I do that, you'll notice that the cart has not really moved at all. So there are no forces acting on this cart in the horizontal direction. So even though the track is moving, well, there was a little bit of friction there, but even though the track is moving, the cart remains pretty much stationary. And that just goes to tell you how little friction there is underneath these carts.